what we're going to be going over here, eigenvectors and eigenvalues, and we're going to be going through an example here. We're going to be fitting these eigenvectors to a certain function here, and then we're going to define a new basis based on our eigenvectors. So the function we're going to be dealing with is a quadratic type of function here, and I'm laying this out here so we have to first calculate our eigenvectors here and eigenvalues, and then we can go into our fitting routine that we're going to be looking at. So this is our function here. It's actually the production function here. But you can see we're raising it to some exponential amounts here, material and labor here, and I'll redefine those as x, y, z coordinates. Okay, so what we're going to do here in this case, we're going to take the second partial derivatives of this function here, and we're going to come up with a 3×3 matrix or a square matrix, which we're going to define eigenvectors and eigenvalues from. So really those are, this Hessian matrix is just the second partial derivatives of this function here, and you can see it laid out here where you got a multivariate solution here based on material and labor quantities raised to some exponential amounts. Okay, so what we'll do here is just take some solution point here for our material and labor. Just say labor here 7.8 some units, material 6.9 some, and then we're going to put those just into our matrix here, and we're going to solve it based and come up with a determinant matrix here just by substituting those solution points for M and L in here. And so we get this block of numbers here, our determinant matrix. And then what we would do with our determinant matrix here, all we're going to do is we're going to take subtract the identity matrix from it. It's diagonal matrix here with a lambda. We're putting in this artificial variable, which is really our eigenvalues here, and we subtract that from our matrix that we have here, and we're going to come up with the matrix shown here, and then we can, with our eigenvalues here, subtracting it along our diagonal axis, and then what we would do is just set this determinant here equal to 0, and we're going to come up with a characteristic equation here that I'm showing here with the eigenvalues in it. Then we can factor out that equation here, so we get our eigenvalues factored out here, everything set to 0, and then we can solve it here, and then you get your eigenvalues here, 3 of them here that I'm showing. Okay, so we got our eigenvalues here, so let's go up and let's look at what we're talking about. Okay, so actually what we're dealing with is this function here, and we're really following around the gradient path, and I'm just looking at a particular point here. That was that solution point that we put into our Hessian matrix here. Okay, so what we're going to do here, we have our eigenvalues here for our matrix. That's what we're showing here, 395, minus 46, and minus 411. And based on a computer solution, you're going to have to come up with some computer software. I'm using MapleSoft, and we can then determine our eigenvectors here, which I'm showing. For each of our eigenvalue here, we have an eigenvector here, x, y, and z coordinates. They just match right up here. So that's what you're going to come up with here. This is what we're going to be working off. And remember, these eigenvectors, they're really unit vectors here, and this is why we're dealing with them. They're less than a unit to 1 here, 0.714, 0.369, and so forth here for each one of those. Okay, so what we're going to do here is this is the first step we're going to take here. After we know our eigenvalues and vectors here, we want to calculate a new basis here to fit those vectors and values here to the function we're dealing with. So what I'm going back to is that our matrix here, that block matrix here for that solution point here. So what you're going to do here, you're going to come up with multiplying some cross terms here, x, y, x, z, x, y, z, and so forth here. So just take along for each of your columns here, just take your x and y and z. We got a 3×3 matrix. And then the same for your rows. First row is x, second row is y, third row is z. So what you're going to do here is you're going to do some cross multiplying. So this is the first step you're going to have to take. So first, looking at row 1 here, all you're going to do is take your 200 times y plus 350 times z. And then you take that quantity times your row x here. And then same thing for your second row here. You're going to take what? 200 times x minus 25.47 times y plus your 20.98 times z. Take that whole quantity here times y, row y. And the same for the third here. 350x plus 20.98 times y here minus 36.71 here times z. then you take that whole quantity here times z, rho z here. So that's what we're talking about here for setting up. We're going to really come up with our equation here. So, okay, I got 1, 2, and 3 parts here to the equation. Then you just, again, you have to use some computer software. I'm using MapleSoft again, and simplify that, and you're going to come up with an equation here. 400 times x times y plus 700 times x times z minus 25 here times x squared plus 41.97 times yz minus 36.72 times z squared. So what we have here is a second degree quadratic function in a 3D plot. No reason we wouldn't have to be looking at this, but this is going to tell us what we're talking about when we're going to be fitting this equation here to our new set of eigenvectors here. So just looking at that, plotting that out, you can see the equation I have here. It's really got two different parts here of the equation. You can see the form here. It's a second degree quadratic equation. And what I've done here, I'm just looking at the normal axis, a 90-degree axis here, not the eigenvector axis, but you can see it kind of fits up sort of nice to the equation we have here. X, Y, and Z coordinates here. Just showing them. Okay, so what we're going to do is let's just go over here and look at this. Same thing here. But what we're looking at is a certain point here that based on our function that we have here. And really, when we're talking about that Hessian or that matrix here, we come up with a quadratic function in this region here, and you can see it shown here, graphed out here, plotted out in 3D, based on curvature here, because we're talking about second degree partial derivatives here. Okay, so based on the function we have, going back to our function here, now we're going to go and we're going to transform this function here. And we're really going to be looking at transforming our plot here, our 3D plot. We're going to try to eliminate any cross products we have in here and get an understanding of what we're talking about with this this transformation here with to our eigenvectors. Okay, so we'll continue on. Okay, now for our conversion. So we've got our eigenvalues here that we've calculated, and for each of those eigenvalues we have a set of x, y, z coordinates here. So for 395 we have our x here 0.714, y 0.369, and z 0.596. And those are the eigenvectors. So that's eigenvector here is telling us the direction that our eigenvalue is going in. And the eigenvalue is just a multiple of our eigenvector here. So we have 3 sets of eigenvectors for each of our eigenvariables. Minus 46 gets this set here, and minus 411 gets this set here. Okay, so what I've got laid out here, x, y, and z, and then just put in our rows again here. Row 1 would be x, row 2, y, row 3, z. Okay, so this is what we have to do here to calculate our new basis or our new axis basis, the new null space here or kernel to fit our equation that we're looking at. So what you're going to do is just take a transpose here. You'll take for your x values, your x, y, and z, we're going to set up a new axis here for each of them. So the x is just going to get the rows, that first row here, minus our 0.714 here, and I'm multiplying it times, not to confuse x, y's, and z's here, let's just say t1, t2, and t3 here. Change the variable names. Okay, so x here gets 0.714 times t1 minus 0.039 here times t2, and then minus 0.07 here, 700 times t3 here. Now, that's for our x variable that we have here. Okay, and then for y, same thing here. Just take that row right across here that you have, 0.369 t1, 0.870 here t2, and 0.328 here for t3. Okay, and then do the same thing here for your z axis here. Just read them right across here and put them in here. 0.596 here for t1, minus 0.492 here t2, plus 635 here for t3. So this is the key here to the whole solution here when you're making this transposing this here. Okay, so we've got our new axis or basis, or they might refer to it as a null space here or a kernel here. Okay, so what you're going to do here, you take that equation that we have calculated previously here based on that. We set up our matrix here and we have that original equation here, quadratic equation that we converted here from our matrix. So what you're going to do here is just take all these x and y and z values here based on t1, t2, and t3. You're going to put them in those amounts here. So for unit x here, it's going to get that whole row here going in the x variable here, and then for y, it's going to get that whole row here, t1, t2, and t3 showing in here, and so on. Same thing for each of the functions here, x, y, and z. And again, you're going to have some computer solution to do this with here. So all I'm doing is using MapleSoft here, and I'm doing a substitution here. And this is really setting up our new eigenvector basis here. So we put those x, y, and z solution, or TL, T2, and T3 here for each of those into our original equation here that we set up on that matrix. And then what you're going to do here is you again make that substitution, and then you're going to have to simplify that with the computer. Computer software, in this case MapleSoft I'm using. And you're going to come up with some new equation here, 395.98 T1 squared, and then so forth, plus 231.85 here, T1 times T2, and then on and so forth here. That's all equal to 1 here. So we made our substitution. We come up with our, based on our basis here, we did a transpose here, rearranged it, assigned our x, y, and z values based on that t1, t2, and t3 coming off our eigenvectors here, and then we plug those into our original equation here that we set up against that matrix, made the substitution, and then based on that we simplified it here, and that's again using some software. So essentially what you've done here, this original eigenvectors here, I'm just showing them, the difference here. The original ones are sitting here, and everything is sitting at 90 degrees. When you're talking about eigenvectors, you get them at 90 degrees here. We got this eigenplane I'm showing here, and then this green one is the key to everything here. The red and the blue are sitting on our plane here, the eigenvectors. Remember, they're unit amounts, and they all have a 0, 0, 0 coordinate. That's the null space we're talking about. And what we've done here, all we've done is we've rotated these eigenvectors down to the no new basis or new null spaces. We made a rotation. The green one gone here, and then the red one is going to go down here. The blue one is rotating off in some other angle. Okay, so anyway, they're sitting at 90 degrees. We made a rotation here. We took our original eigenvectors and we rotated them to the new eigenvector basis that we come up here. So again, that's what we've done. And look at over here on this side, same thing, just looking at it from the other side. But everything is sitting at 90 degrees here. The new eigenvector basis is also sitting at 90 degrees here. The red and the blue and the red here at 90 degrees, and the green one here is at 90 degrees to the blue and the red, and that's the case here for both our rotated eigenvectors and our original eigenvectors. But you can see here, we rotated them down here. Just looking at the green one, and then the blue would have rotated down and so forth. Again, they got a 0, 0, 0 starting point here. Remember, those are just the unit vectors we're talking about. So the eigenvalues are going to follow the same path here. They're just the multiple of our unit vectors here. So we got this 90, they're 90 degrees to some plane that we're talking about. Okay, so let's go up here and let's look at what we've done here. So just looking back at our original quadratic function here that I've plotted here. Remember what that matrix we laid out, our original equation, setting up our x, y, z coordinates here, cross multiplying and so forth. So I didn't want to confuse this here by taking the the eigenvectors that we had, original ones, and then put the rotated ones on top of it, because they can become pretty messy here. So all I'm doing is looking at it from our normal x, y, z axis that we have here. And this is that original quadratic function. You see how it fixes up here. Here's our 0, 0 point here. And this is, I don't know, x or y here. Z is going up and down in green here. it sort of fits our equation. It looks kind of nice here in an equation. But what we've done here, and what you're trying to do when you're making these transformations, you're just rotating those eigenvectors here and eigenvalues as well here. But we have this axis or a null space here. So you can see here we rotated them just based on our normal ones going straight across. Now it's going down like this. And this is really fitting our equation better here. It's really fitting our equation better. So you got the 3D axis here. Okay, so this is just the original amount. Now, what I've done here, I plotted a newer revised function here. I plotted that here. So and you can see the difference between that, our original quadratic function, and our new revised function here. Let's just go back and let's look at what we're talking about here. Okay, so let's go back here. So this was that original equation here that we have based on those cross multiplying, setting up our x, y, z coordinates here. And that was the original one that we're looking at here. And then the new one is this whole function here with the t1 squared and t1 times t2, t1 times t3, and so forth, t2 squared. Now the object here was to get rid of our cross terms here when we set up this new function here that we have based on the old ones. But I wasn't quite able to do that based on the function we have. But that's generally what you'd be doing here. Okay, so we've got these two different functions. So let's go and let's see which one is fitting better here. Okay, so now we're sitting over here. Here's the new revised one, and you can make the comparison to the original function we have here. And supposedly this is going to fit. The reason we did this transformation here at eigenvectors is to fit our function and our axis better here. So you can see here, just based on our normal x, y, z axis, you can see it here. But you can see the profile here, how it's changed here. But now, and you can see the x, y, and z here, green, red, and blue here. But now, this over here is the rotated eigenvectors here. And supposedly these are going to fit better. They're going to fit our equation better. We're fitting up our eigenvectors to our equation here, to that solution point. And we got this axis or this null space here fitted to our revised function. This is the revised function. You can see you've taken, if you compare it to the original function we have here, we got some curved surfaces and so forth here. But with the new function, we fitted it up here, and by putting in that new function, we're trying to fit it up to those axes very accurately here. And doing it pictorially, and that's what we're doing here when we changed our eigenvalue basis here. We're trying to get a more linear relationship that we can understand, and that's what the point I'm trying to make here. Okay, so this was our normal axis here. Here's our rotated eigenvectors, and you can see they kind of fit in those planes. I can't show the whole eigenvectors here because I can't rotate it here in this still picture here. And then if we went down here, you can see it looking sort of into it here. And that rotated basis here is showing green, red, and blue. And they really do follow the surfaces that we have here. Try to follow those surfaces very well. Okay, and then if we went over here, see the same thing. I'm just a different view here. You can see the same thing. But these red, or green, red, and blue here, those are the rotated eigenvectors here. Okay, so now let's just go on and we'll look at one other thing here with the eigenvalues. Now for our eigenvalues. Now remember, they're just the scalar length of the eigenvectors, and really the direction is the same as our eigenvectors here. Okay, so for our eigenvalues, we're going to have three of them here. I got two shown by our yellow arrows here, and those are the largest of the vectors that we have here, 395.52 and negative 411.46. And those are the large ones here, and they land on what we call the eigenplane, or our plane here, vector plane. And the other one is our shortest one here, shown in red here, and that's at minus 46.250. And really, that's the one that you're usually concerned about here. This is where you're looking for the change. You're going to have two of them that make up a plane, and then you got a third one here in our case here, which is where our change comes in. And the plane here is really tangent to our function here, and this red one here is perpendicular to the function we have, or at a 90 degree to it. Okay, so just to understand how we come up with our coordinates here for eigenvectors here, so let's just look at the one here, 395.250, and we got some values here that make up its x, y, and z coordinates, and that's based on its eigenvector here. Now, I'm just, for our eigenvectors I'm using here, I'm just using the original ones, our original basis, not the rotated ones. Okay, so just understand it's x, y, z for eigenvector, so you take 0.714 times 395.52, and you're going to get 282.40. And then the next one, that's for the x coordinate, and then our y coordinate here would be 0.369 times 395 here, and you're going to get 145, and then that's for a y, and then for a z here, take 0.596 here times 395, and you're going to get 235. So those are the x, y, z coordinates for our eigenvalues. And remember, the eigenvalues are just a scalar length, scaled up here in this case, based on our eigenvectors, and they're in the same direction here. And we do the same here for the other two here. We got the x, y, and z coordinates, and based on that, taking your eigenvector for each one of those times your eigenvalue, that gives you your coordinates. Okay, so that's what we're talking about with eigenvalues. Now let's just go and let's just look at it in 3D here. Okay, so let's just move down here. So let's look at our original matrix, that quadratic function that we set up with those cross products here. And the reason I'm plotting this out here is just to get a little better understanding and understand what we're looking at here when we look at those matrices. So rather than just look at numbers, we can look at profiles here, or plots here. So what you would do here, you'd want to take and you'd want to plot out that take your original matrix quadratic function, whatever that is, you'd want to plot it out here in 3D. And in this case, I'm just using the original eigenvalue basis here for the axis, or the eigenvalues that we're looking at, or the null space. And we're talking about a null space, we're just talking about the space starting at 0, 0, 0 point here, this yellow point here. Okay, so this is our matrix here, just showing out here that original matrix that we have here. And what I did is I just overlaid, or I'm slicing through it, showing where that eigenplane or those eigenvalues fit into that matrix here. Can't rotate it around here, it's just a still picture. Okay, so this is our original matrix here. Okay, so moving over here, same thing. See that eigenvalue plane here, those two yellow vectors here, and that little red one is pointing down in this direction here. Same as over here, yellow here, little red one here. Just to get an idea. All this is, it's good to do this to get an understanding of what is going on with your function here. And this happens to be my particular function. Okay, so that's for our original matrix here. And just remember, our eigenvalues here are just based on our original eigenvectors that we didn't rotate. Okay, so let's go up over here. Okay, now this is our new revised function here that we fitted here to the revised function that we fitted here to our function based on this is the revised function here, but these eigenvectors here, or our eigenplane here, value plane, or values here, those are just the original ones, not to confuse it. You wouldn't really be able to tell the difference between this and what the new ones are, but you get sort of a fit up here, which you can see here. So we got those two yellow vectors here, and then we got some 0 point here. And the point is here, with this new revised function, it's probably not as neat to look at as the original ones here, but what we're trying to do here, we're trying to level out those planes here. We're trying to come up with a point here where you can look at those planes and get a better understanding of what they're doing. I'm linearizing those planes. Okay, so that was shown here. Here's our plane here, our two vectors, the yellow. And then if we go over here and look at it from looking into it here, we got our two yellow vectors here. And here's our plane. And here's that matrix, that original, the new revised function. That's that matrix that we set up. Okay, you see it here. And then if we finally just go down over here, kind of get a side view of it here, just to see the power of computing here with, in this case, MapleSoft here. So I was able to put in my eigenvalues here based on those its plane here, and I can slice it right through into my the new revised function here, quadratic function. Actually, we tried to take the cross product out of it, but not totally able to do that here. But nonetheless, gets you some feel here. The only reason I'm showing this is to get some feel. And then if we finally move over here, just looking at a side profile here, just remember these surfaces here, that's our actual matrix that we're talking about, the matrix here. And there's that plane again here. And there's one of our eigenvectors, one of the large one, the yellow one over here. Okay, so you get to see it here. Moving back up here maybe just one last time. So you can get a side profile here, and then is looking into it here. And what we've done here by this new revised function, it's a little hard to see, but we tried to linearize it. We take the quadratic form out of it best we could here, and we tried to linearize it. And by linearizing it, you can get a better idea what you're doing with it here. And then with the new eigenvectors and new eigenvalues, you try to rotate them into the plane, into your new revised plane here. You try to match everything up. In this case, I'm just using my eigenvalues here based on my original eigenvectors. But it wouldn't be a whole lot different had I looked at the other one here. It would rotate it like we did here for our eigenvectors. We rotated it around here, but it gives you an idea what's going on here. So here's our matrix. Here's our eigenvector plane. Okay, so that'll summarize our discussion.